Alright, what's going on, guys? Today we're going to be doing our lesson 2 of unit 2, and we're going to be investigating another type of rate of change. So in the last lesson we talked about the average rate of change, which is the slope of a secant line, and this time we're going to be talking about the instantaneous rate of change, which is going to be a slope of a tangent line. So you're going to soon be able to learn what a tangent line is, and hopefully you can understand how do we actually estimate this rate of change at a particular value of the independent variable with whatever math we have unlocked right now. Let's go ahead and get started. So we have to investigate this. So a small pebble was dropped into a 3-meter tall cylindrical tube filled with thick glycerin. A motion detector recorded the time and the total distance that the pebble fell after its release. The table below shows some of the measurements between 6 seconds and 7 seconds after the initial drop. So they gave us a little table here. And first, they asked us to calculate the average rate of change in these distance that the pebble fell during each of the following intervals. So this was everything from our last lesson. Hopefully you're able to do this on your own, but I'll also be doing over this with you just for a quick review. So let's go ahead and do this. So note that our average rate of change formula should be, the distance dt and dt final dt, let's say dt2 minus dt1, and all of this is over t2 minus t1 over t2 minus t1. So right away we have 6 and 6.4, so that would be 235.41 minus 208.39, and this is over 6.4 minus 6.0. So we have something of 27.2 over 0.4. Sorry, 27.02 over 0.4, which will get us 67.55. And then obviously we cannot forget our unit, so that's centimeters per second. And for our second one, we will have 6.4 and 7, so we'll have 277.84, 277.84 minus 6.4, so 235.41 over 7 over 7.0 minus 6.4. So we would have we'll have 13 point, sorry, what? Oh no, I'm doing 3. Oh, okay. So I skipped number 2. So let me just write this down. 1. Let's do 2. We'll have 3 here. Alright, so let's go ahead and do 2. So I skipped 2. So 6.4 and 6.2. So 6.4 and 6.2. So at 6.4 we'll have 235.41 minus 6.2, so 221.76 over 6.4 minus 6.2. So that would equal to 13.65 over 0.2, which will get us 68.25 centimeters per second. Let's do our 3, so our calculation here. So 277.84 minus 235.41, and everything over 0.6, so 42.43 over 0.6. And then this would get us 70.72 centimeter per second. And then let's go ahead and check our 4. So that would be 6.8 and 6.8 and 6.4. So let's see, 263.46 minus 6.4, so 235.41 over 6.8 minus 6.4. So that would go ahead and get us 28.05 over 0.4 over 0.4 which will get us 125. And then finally we'll have number 5, which is 6.4 and 6.6. So we will have 249.31 minus 235.41 over 6.6 minus 6.4, and then that will get us 249.31 minus 235.41, so 13.9 over 0.2, 13.9 over 0.2, and that will finally get us 69.5 centimeter per second. So don't forget our unit. So here we have we have our list that they want to calculate. So use our results from part A to estimate the instantaneous rate of change in the distance that the pebble fell exactly at t equals 6.4 seconds. Explain how you determined your estimate. So here you might be able to have some, different interesting thoughts. You might be able to get some different ways from how the textbook intended you to do it, which obviously I'm really happy for you. But as we are trying to observe our answers from this, let's see what we can really get. So we have 6.6 to 6.4, 6.3 to 6.4, 6.4 to 7, 6.4 to 6.8, 6.4 to 6.6. So notice that every single one of these values, we have 6.4 in them. So, but is this really the best value? Right? If you think about it, is this really the best value? So basically we have learned a secant line, and we kind of want to do anything we can to get that secant line approximation back. So why don't we use an interval that has 6.4 within them? So let's say this graph is something rather linear. So let's say it's something like this, right? Hopefully 6.2 is right here, 6.4 is right here, and 6.6 is right here. Obviously this is not linear, as you know, because our rate of change isn't constant. But let's say it's something like a curve, like a smooth curve. Something like this. And then we have 6.2 here, we have 6.4 here, we have 6.8 here. So hopefully we could do we could check the slope of the secant from 6.2 to 6.6 and use that hopefully to estimate what the slope at 6.4 is. And that's how we're gonna kind of do it right now. So let's go ahead and try this. So let's estimate let's estimate um let's estimate the instantaneous rate of change by having values close to t equals 6.4 on both sides. Okay, so with that, let's go. So we're using our interval 6.2 is less or equal to t less equal to 6.6. Yeah. So let's calculate this, just pretty much the same as what we did A. So let's go ahead and do 6.6. So 249.31 minus 221.76 over 6.6 minus 6.2. So you're getting 27.55 over 0.4, which is going to give you 68.875 centimeters per second. And then we're going to round that, so let's round that to 3 sig figs. Technically, we should round only to 2 sig figs, but that doesn't really matter. So let's do 68.9 centimeters per second. So therefore, our best estimate of the instantaneous rate of change at t equals 6.4 is 68.9 centimeters per second. It's approximately 68.9 per second. Okay, so let's go ahead and look at this. So find the average rate. Calculate the average rate of change. So we have calculated. So we have already calculated that. So let's go ahead and look at this. So we use this exact interval to estimate. So our answer is the same as the estimate in part B. Okay, so why do you think each of the interval you used to calculate the average rate of change included 6.4 as one of the options? Right? So because our goal is to estimate the instantaneous rate of change at t equals 6.4. By using intervals with 6.4 as one endpoint, we can calculate the average rate of change very close to that exact time. And this is why we always have 6.4 in one of this. So now, E, why did it make sense to examine the average rate of change using time intervals on both sides of t equals 6.4 seconds? Which of these intervals provided the best estimate of the rate of change at t equals 6.4 seconds? So here I'm going to give you my reason. It is better to use intervals on both sides because the instantaneous rate of change at t equals 6.4 is best estimated by examining how the distance changes just before 6.4 seconds and just after 6.4 seconds. So notice our slope right here. If this curve was really something like this, here will be more flat and here will be more curvy. Here will be more straight, more steep. You have a steeper slope. So it kind of balances each other out. So I drew that graph for you just real quick. So because we wanna balance the estimate of the slope at that point. So by having an interval centered at 6.4, this provides a decent estimate. Okay, so let's not get too ahead of ourselves, and let's go down to F, part F. So um, why does the interval, even though 6.4 is not an endpoint of the interval used in the average rate of change calculation in the part C, explain why this calculation gives a reasonable estimate for the instantaneous rate of change. So I just kind of explained it, so it's kind of the same reason as we did here. So we want to balance it out. So because 6.4 is not an endpoint, it is a midpoint, and therefore the interval used data equally spaced before and after 6.4. So this means because we have data centered around 6.4, the effects of changing rate before and after 6.4 balance out pretty well. So having 6.4 as the midpoint rather than an endpoint balances out the rate of change before and after 6.4 seconds. Therefore, we would have a better estimate. Okay. G. Using the table of values given, is it possible to get as accurate as estimated rate of change for t equals 7.0 seconds as you did for 6.4? Well, obviously, no. The reason is, G. No. The reason is that 7.0 seconds is the very last time value in the table. There are no data points after 7.0 seconds, so we can only use 7.0 seconds as an endpoint rather than a midpoint. Okay, and there we are done our our introductory math, sort of. So we can conclude that to calculate an instantaneous rate of change, we kind of have an interval, but we want that interval to be pretty small, to be very close to the point that we want to estimate. Because we picked the smallest point near our interval, right? We picked 6.4 at the exact time second, so we picked 6.2 to 6.6, right? That's pretty small. It's pretty small considering how fast time passes. So we want to get as small as possible, and we still want to use a secant line because we don't know how to do calculus just yet. So right now we have a pretty decent approximate. Let's go ahead and move on to our examples. So selecting a strategy to estimate instantaneous rate of change using an equation. So we have 3 examples today. Go ahead and put these ladies out. So first, the population of a small town appears to be growing exponentially. Okay, that's pretty good. Town planners think that the equation P of T is P of T multiplied by 35,000 times 1.05 to the power of T, where P of T is the number of people in town and T is the number of years after 2000. So notice that T is not time. T is not time. It's the number of years after a specific time frame. So the number of year of 2000 right here. So models the size of the population. Estimate the instantaneous rate of change in the population in 2015. Okay, so what are we going to do? Right? What are we going to do? So there are many ways that we could do this. We have 2 different strategies obviously here. We could do a preceding interval, so we have 14 to 15, and then we could also use a following interval, which is 15 to 16, but obviously we know the best interval is from 14 to 16, right? But right now, let's think ahead of ourselves. 14, 15, 14 and 16. So let's see. Let's write this out. 14 less than t, less or equal to t, less or equal to 16. Is there any way we get more precise? What if we smaller this? Because this is a function. We could plug anything we want in there, right? So what if we go to 14.5 less or equal to t, less or equal to 15.5, right? What if we want to get even smaller and we do 14.8 less equal to t less or equal to 15.2, right? We could get even smaller. And as we get smaller, our estimate should technically be better, right? Because we're getting closer and closer to the point. Let's just draw this graph out. Obviously it's an exponential function, so we know how it goes. It goes something like this. So let's say right here we'll have our t equals 15. So t equals 15. T equals 15. So obviously this is 2015 because t is 15, right? 2015 here. So notice when we have 14 and 16, so we're looking at 2014 to 2016, we'll have a pretty long secant line that doesn't really touch t equals 15. Right, so we estimate this secant line, and we use this secant line to estimate this instantaneous rate of change at t equals 15. So what if we use 14.5? So 14.5 right here and 15.5 right here. And now we use a slope. We look at this and be like, oh wait, this get closer to how this graph originally acts, right? Because if you zoom in on this, this secant slope would be something like this, while the real graph would be something like this, right? Something like this, something like this. It gets pretty close, right? That's pretty close. But once you look even closer, so let's see 14.8 and 15.2. So it'll be right here. Right here. Wow, that's really close, right? Look at this. This right here, this will look like something like this. So the secant line will look something like this. Something like this. While the graph originally looks something like this. That's like exactly on it, right? So as we close our intervals smaller and smaller, we seem to be getting a better estimate. So let's just check that with the function because we can plug anything in there, right? Anything we want. So go ahead and just use our. Let's do the original one. So P16 minus P14, and we'll have everything over 16 minus 14. Right? Let's just do the first one. Let's see how bad this is. So P16 will have 76,401, and then minus P14, where there's 69,298. So 76,401 and 69,298. This is all over just 16 minus 14, so 2. And then the top will get us. So this will get us around 3,552 people per year, approx. Right. So our population is increasing by around 3.5k a year. Okay, let's use a better interval. Let's go ahead and use first interval. Let's go ahead and use our second interval. So second interval. Second interval. So P of 14.5 minus P of 15.5 minus P of 14.5, and this is O over 15.5. Oh, minus 14.5. So this is O over 1. So P of 15.5, that's around 74,559. Minus 71,009. Right? And then this is just over 1. So that will be around 3,550 people per year. And this is also approximate because we rounded our value here. And now we could get really close. So this is your mission. Your task is to check this and see if it gets any closer. But right now, I'm satisfied. Because look at this. When you have this interval, your change is around 3,552, 3,552. And when you have this smaller interval, you have 3,550. So you closed out by just 2 people, right? They're very similar, but as our center interval, as it gets really, 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 really small, our change gets smaller and smaller, right? Our change gets smaller and smaller. We'll see that this is not a big jump. It's just 2 people per year. So we're kind of fine with this, but we have to acknowledge the fact that as we close our interval, it seems like we're getting better approximates. Okay, so let's test this out with our second example. So the value of a cubic crystal grown in a laboratory can be modeled by V of x equal to x cubed. V of x is a volume measured in cubic centimeters and x is a side length in centimeters. Estimate the instantaneous rate of change in the crystal's volume with respect to its side length when the side length is 5 centimeters. Okay, so this is really similar, and let's go ahead and use another. We're gonna use another. Let's do another. Let's do another squeezing with centered intervals. But we are also going to be introducing an algebraic way, right? There's an algebraic way to do this. So first of all, I do want to introduce the algebraic way, but I just kind of want you guys to go ahead and know how this really works, because this is a quite complicated topic, and understanding it is quite crucial to calculus, right? So we have this graph here, and this isn't our graph. This isn't a cubic function. It's a quadratic function, but we can kind of see what's going on. What's this graph told? So let's say we have a random value a, and this is the value that we kind of want to approximate. We want to approximate the rate of change at A. So let's do so how do we find the rate of change at A? Well, we want to estimate using an average rate of change, right? We want to that's what we've been doing. So right here A is an endpoint. So we will have this y value right here, which is f of A plus h, right? F of A plus h. F of A plus h is our y value here. This is our y value, right? F of A plus h. And obviously, what's our y value here? This would just be f of A. And we have a secant line connecting these 2 points. So the average rate of change from A plus A from A to A plus h will simply be what we have here. So delta y is f of A plus h minus f of A. And this is our slope, by the way. Slope. And the bottom is just h, right? Because from A so let's just do the bottom as well. So A plus h minus A. And that would give us f of A plus h minus f of A is just over h. Right? We have this. We're done. So this seems like this is a difference quotient, by the way. This is how we can estimate where h of it's a very small number. This whole expression is called a difference quotient. So we're gonna be checking. So first, for this question, we're gonna be using our difference quotient and see what we have. But at the same time, we're also gonna be looking at our interval. Let's see if if this is any close to what we have. So let's go ahead and do this. So we could pick h as any value, right? I'll erase all of this math. But you could definitely save this picture. This is a pretty important picture. I like this graph a lot. This is perfect for explaining. So what we want to do essentially is we want to move this h as small as possible. So we want to move this h along the graph. So let's say we have this graph. Oh, not what I intended to do, but let me get it back. Let's get you back. So let's say we have this graph, right? So what I intend to do is essentially move down my point along the graph. So let's say I have A and H here. So this is A, this is H. Essentially, I want to close H to over here, over here, over here. Finally, I want A to be so close to H. I want it so close. Look at this. This is A, right here. This is A. I want H to be somewhere right here. I want H to be so close to it. I want it to be so close to it that we can estimate the slope of this very small part. And by drawing a secant line, it looks like our secant line is the exact same thing as the graph originally. So let's go ahead and do this. So let's pick an H value. What's a very small value? Let's say 0.001. Or 0.01 should be fine, but we could do 0.001. Let's do that. So set H equal to 0.001. That's pretty small in my opinion. Let's go ahead and plug it into our different quotient. Hopefully you remember what it was. So it was A plus H minus f of A plus H minus f of A. So let's write it out. So estimated rate of change would be A f of A plus H minus f of A over this everything over H. Okay, so f of A plus H. So we're looking at our point A, our focal point A is 5 centimeters. So A plus A plus H is 5.001. That's pretty small in my opinion. Don't you think that's really small? So let's check it out. So we'll have 5.001 cubed, right? We're plugging this in. So f of 5.001 minus f of 5, and this is all over 0.001. You will notice that the top doesn't have a huge change, right? But because the top doesn't have huge change, but because we're dividing by 0.01, no matter how small the top change is, it gets amplified by a lot. So let's just plug it in. Let's just plug this in. So 5.001. So 5.001 to the power of 3 will get you 125. This is going to be very hard. 125.075015. And obviously we know 5 cubed is just 125. Minus 125 over 0.01. Wow, that's really small. So essentially, we're going to be looking at 0.075015 5015 over 0.01. So we're looking at, but because it's really small at the bottom, it amplifies. So the bottom becomes now, the rate of change becomes 75.015. And obviously we have to think about our unit. So it's centimeter cubed per centimeter, right? Because we see the instantaneous rate of change in crystal's volume respect to its side length. So the side length is in centimeters with respect to a side length at our x-axis right here, and then the crystal's volume is our responsive variable, so our y value. So it's cm cubed over centimeter. So this is what we got. We estimate that the instantaneous rate of change the crystals in the crystal's volume with respect to its side length when the side length is 5 centimeters is around 75 is 70. Well, it's not around, but we didn't round at all, so 75 centimeter cube per centimeter. So let's go ahead and check with our interval that we used. Let's pick an interval. Let's pick a pretty small interval. Let's say what interval is pretty small? Let's do so unlike last time, this unit is pretty large. So let's go ahead and do 4.9 is less or equal to 5 is less or equal to x is less or equal to 5.1. That's pretty small. Right, how about we actually let's go even smaller. So 5.99 and 5.01. This should be really, 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 really small. Let's go ahead and use this interval. So we will have obviously our rate of change formula, our average rate of change. So f of 5.01 minus f of 4.99, and everything is over 5.01 minus 4.99. So what we have? So f of 5.01, what is that? So f of 5.01 is 125.751101 501. And then f of 4.99 is 124.251499. And everything is over 0.02. So we will estimate this to be around 75.00001 centimeter cube per centimeter. So we notice these values. They're so close, man. They're so close. They're like almost the exact same thing. Right? They're really, really close. So we could see that these rate of change are really similar, and it looks like our algebraic way does seem to work somewhat. Let's go ahead and move on to our next question. Selecting a strategy to estimate the instantaneous rate of change again. So the following table shows the temperature of an oven as it heats from the room temperature to 400 degrees Fahrenheit. So we could use 2 ways, obviously 3 ways. You learn a lot of ways, but let's go ahead and work with an interval. So estimate the instantaneous rate of change in temperature at exactly 5 minutes using given data, and estimate the rate of change using a quadratic model. Whoa, what is that? Let's not get too frightened. Let's go ahead and move into this. So let's choose some time interval, any time interval that you want. Let's go ahead and just pick the closest time interval. Let's go 4 and 6. Why not? 4 and 16 just sounds like a nice interval to have when we estimate this, right? Doesn't it? Let's go ahead and do this. Let me copy a text box here. Copy the next one. So let's copy in here. So A, estimate using the interval, because we don't have a function, right? We don't have a function, so our algebraic way is out of the door. So let's go ahead and just do this. So you using the interval 4 is less or equal to x is less or equal to 6. So from 4 to 6. So obviously we will have um, f of f of 6 minus f of 4, and this is O over 2. 6 minus 4. So f of 6 is 310 minus 250 over 2. And don't forget your brackets, because our order of operations will be messed up. So and this everything is gonna equal to 60 over 230, 30 degrees Fahrenheit per minute. Right, so our temperature is increasing at 30 degrees Fahrenheit per minute, and then as our center interval is around 5 minutes gets smaller, it appears that the average rate of change in the temperature of the oven gets closer and closer and closer to 30 degrees Fahrenheit per minute. So now, let's go ahead and see what the quadratic model is. So let me open Desmos. Let me just quickly change this to Desmos. Let me just screen share my Desmos for you. Hopefully I'm able to screen share Desmos, but if you have a TI calculator, you should also be able to just do this with the TI. So essentially what we're going to be doing is we're going to be inputting all of our data values. Let me move this here. So let's move our this to Desmos graphing calculator. Oh, it doesn't seem to be working, so drag it here. So now we should have our Desmos graphing calculator. So we have this Desmos calculator, pretty good, pretty cool. But what do? Right, we have all of this data that we were able to get in our entire example. So let's go ahead and get a data table. So what do we have here? We have 0, 70, 0, 70, 1, 125, 0, 70, 1, 125, 2, 170, 2, 170, 3, 210, 4, 250, 3, 210, 4, 250, 5, 280, 6, 3, 310, 6, 310, 7, 335, 8, 360, 9, 380, 380, and finally we have 10 and 400. So this is our entire table. Right? Okay, we were like, okay, fine, this is pretty good. It looks pretty neat. So what do we do here? So let's see. Let's get smart. Let's do a linear regression, but instead of picking a linear regression, why don't we do a quadratic regression? Wow, quadratic regression. I know some people are taking data. Some of you are taking data. Hopefully you guys know what it is. And you guys look at this. Look at this. Oh my God, this quadratic data is perfect. Right, this quadratic model is perfect. Look at every single point. They seem to be lying pretty close on the data. Right, it looks pretty good. It looks pretty good. But what does that mean? What does that mean? That means we have a function now. See, Desmos provide us with this beautiful equation that we're able to use. Let's go ahead and use it, right? We have this equation. Let's put it here. Wow, let's put it here. Let's put it here. This is pretty big, right? We have an equation. It's pretty good in my opinion. So we can use this quadratic equation, and obviously, let's go ahead and calculate the rate of change using our algebraic equation. Right? So since we want x to be centered around 5. Obviously, I can't type anymore here. That doesn't really matter. So we want our x to be centered around 5. How do we do this again? How do we do this? So we would have f of x plus 0.001. We want x plus h, right? We want very small. So 5 plus 0.001. And we want this to minus f of 5. And we will have this really, really small number. But we're going to divide it by our h value, which is 0.001. We will see, wow, 32.27. We just got it. We got it. This is what we have, right? This is our answer. So using this quadratic model, we're able to estimate that the instantaneous rate of change of temperature is around 32.27093.182 degrees Fahrenheit per minute. Wow, this is incredible considering we didn't even use calculus. This is all with algebra and with the graph and with everything that we have. Although you're not going to be using Desmos on your official exam or any quizzes, but it's really nice to see what Desmos can really do. Let's go back to our, let's leave this side. Let's go back to this. And I'll summarize our lesson up. So in summary, the instantaneous rate of change of the dependent variable is the rate of change with the dependent variable changes at a specific variable, at x equals to a. And the instantaneous rate of change of the dependent variable in a table of values or an equation of the relationship can be estimated using the following methods. So a series of preceding and following intervals. Right here we talk about this. This is really good, a series of centered intervals. So we calculate the rate of change by picking endpoints. Guys, if you need this summary, it's on page 85 of your textbook, just saying. And then finally, we will have our algebraic difference quotient and a general point to calculate the average rate of change at the location of that. So the best estimate, they talked about it here. The best estimate for instantaneous rate of change occurs when the interval used to calculate the average rate of change is made as small as possible. Alright guys, I hope you enjoyed this lesson. Oh, don't forget, your homework is on page 85, 86, and 87. The question and 88. So a lot of homework. So hope you guys get some practice in. They're pretty much similar to these examples that we've been going through. There have been 16 questions. Hope you guys can do all the even or odd numbers. Pick yourself. Spin a die. Spin a roll a coin. Do whatever you want. Anyways, hope you guys have a great day. And next lesson, we're going to be exploring instantaneous rates of change using graphs.